Recall what we completed in example 7. We found that 4c plus 5 times 2c minus 1, when we multiplied those two binomials together, the result was 8c squared plus 6c minus 5. What that means is we took that product and we expanded it into this trinomial. In math, any operation that we can complete, we can work in the opposite direction. So now what we want to move towards is talking about factoring trinomials to arrive at the product of two binomials. So rather than expanding, just taking that process backwards. We'll start off by looking specifically at the case where our leading coefficient is 1. It's one of our easiest cases for factoring besides simply just factoring out a GCF. So we'll start with factoring a squared plus 14a plus 48. Since our leading coefficient is 1, that's a key for our technique in these next few examples. What we want to do is look at that value for the constant at the end of our polynomial and list out its different factors, two different numbers that we can multiply together to get 48. So examples would be 2 times 24, 4 times 12, 6 times 8, and we just need to keep generating that list until we have a pair that adds together to equal 14, that value for the middle term. So we'll look at adding these together. 24 plus 2 would give us 26, that's not the number we're after. 4 times 12 would give us 16, that's not what we're after. 6 plus 8 though would give us 14, and that's exactly the value we want for that middle term, meaning we can factor this expression as a plus 6 times a plus 8. We won't do this with every example, but I would encourage you strongly, especially on a quiz or a test, to check your work. You can always do that by taking your factored expression and expanding it back out. Since we're multiplying two binomials, we'll FOIL to get a squared plus 8a plus 6a plus 48, which will become a squared plus 14a plus 48. Since we can expand that out and get back to the original problem, we know we have the correct factored expression of that polynomial. We'll do the same thing in example 13, except that now our last value is negative. So we'll think about factors of 32, pairs of numbers we can multiply together. For instance, negative 2 and 16, but also negative 16 and 2, negative 8 and 4, negative 4 and 8, where again what we just need to do is generate a large enough list of those pairs until we find a pair that adds up to that term in the middle. In this case, negative 2 and 16 will give us 14, which is not what we're after. We'll get negative 14, which is not what we're after. Negative 8 plus 4 will give us negative 4, which is not what we're after, but negative 4 plus 8 will give us positive 4. So that's the pair that we want. Those two values multiply together to equal that constant at the end and add together to give us that term in the middle. So our factored expression in this case would be x minus 4, x plus 8. Which again, we could check by expanding that back out. Examples 14 and 15 look a little bit different than those last two because now what we have is a coefficient not equal to 1. But we haven't discussed how to factor a type problem like that yet. In this case, what we want to use is a simpler trick than what we move on to next, and that is to go back to that idea of finding a greatest common factor. So here, each of our coefficients in example 14 are divisible by 2. So we can start off by dividing out that factor of 2 to make our polynomial y squared plus y minus 12. If there is a GCF that you can factor out, check for that first. And now we've taken a problem that would otherwise be more complicated and made it match up with the previous two examples that we just discussed above. We'll look at negative 12 and try to find pairs of numbers that add together, multiply together to give us negative 12, but add together to give us positive 1. In this case, if we took negative 3 and 4 and added those together, that would give us positive 1. So that's the pair we're after. If you don't get that pair in your first guess, we just continue to try combinations until we get the right one. But in this case, we could factor this as 2 times y minus 3 times y plus 4. And since we factored out that 2 at the beginning, it's absolutely critical that we still include that in there so that we haven't changed our problem. Similarly, in example 15, we'll start off by pulling out that greatest common factor, which in this case is 3, making our polynomial z squared plus 8z plus 15. So we need to consider factors of 15, which in this case could be 5 and 3, which do add together to give us 8. So our final factored expression here would be 3, since we need that GCF that we factored out, times z plus 5 times z plus 3.